logic. Chapter 2. All right, we're going from where you're reading stories, pulling out the objective function, pulling out the constraints and writing them, to now seeing how they're solved, how the computer program will solve it manually. Now, you've got to get through this chapter 2, get through the next quiz, and you don't have to worry about this ever again. This is all about use, understanding when now, after this chapter, the outputs will all be by computer or Excel. And this chapter is all about you understanding what's happening on the computer program and what's happening on Excel to get that optimal solution. This is what's happening manually. And this is how I used to have to do it before, because Excel wasn't invented yet, and these softwares weren't invented yet. And so I had to do it what you're about to learn, this way. So, here you go. Here's all these are all the slides you read before you got here. One second. Oh, wait, what am I doing? Crazy? Man, forget all that. Let's go over here. I want to refresh the map before we get into this. I know some of you go, oh, I don't need to refresh this. But believe me, there's people around you who are going to be very appreciative I refresh this because they haven't seen it in a long time. I'm going to show you, I'm going to write 2 equations. I just put them up here. I'm going to change the variables. No, I got to make them the same. x1 plus 3x2 less than equal to 19. There's one equation. x1 plus x2 less than equal to 8. Okay. These 2 equations can be graphed. And we're going to learn how to graph them. But when they're graphed, somewhere along the way, these 2 lines, if you extended them, cross. And where they cross, there's a point. It comes off the horizontal axis and the vertical axis. Horizontal axis, we're going to make x1. Now this isn't going to be on the camera over here, but we need the space, so oh, you guys, man, you're going to hate that. We're going to create more space then. All right? Anybody needs to leave there, just try to get away with this. All right, you ready? Put a graph over here. It's going to be sloppy, but this is going to be the x1. Here, I'm going to make this x2. You know this is x1, but I'm going to have to go farther. That's why I'm not putting the x1 there yet. When you have lines on a graph and you're saying, I want to know that point right there where these 2 lines are crossing, don't rely on looking at the graph and go, oh, that's 6 and that's 5. No, that could easily be 6.163, 5.227, and they just look like they're 6 and 5. You have to take the 2 equations that those 2 lines are formed by and either do the substitution method, the addition method, or the subtraction method to find out exactly what those 2 points are where they cross. Now I'm going to demo all 3, but you only need to use 1. I'm demoing all 3 so that you can decide which one you find easiest. One of them might reach out at you and say, this one I understand. Write big notes on that. Even put yourself a note. Use the blank method so that you remember this is the one you found easiest. Because all of these will get you the same exact correct answer. Are you ready? Starting with substitution method, you look at the 2 equations and you say, I need to get one of the variables, x1 or x2, in one of these equations all by itself on one side of the equality. Which, by the way, just for visual, I like switching these to equal just for this process until I'm going to graph them. When I graph them, I got to go back to less than equal. But for this process, I like to make them equal because it's where the lines pass. Not all the numbers around those lines, where the lines themselves cross. So I'm going to use the second equation because then I don't have to divide by anything to get the variable all by itself. So all I got to do is either subtract x1 on both sides or subtract x2 on both sides, and I isolated a variable. So I'm going to subtract x2 on both sides. x1, all I have left over here is x1 because these 2 cancel each other out. And then over here, though, I have 8 minus x2 because I subtracted it on both sides. Whatever you do on one side, you got to do the other. Now that I isolated a variable, I take what that variable equals and replace that variable in the other equation I didn't use. Remember that. It's not the same equation you just used. The other equation I didn't use. So I'm going to make x1 in this other equation right there equal to 8 minus x2. So now it's 2 times, instead of x1, 8 minus x2. Then I finish the equation. Plus 3x2 equals 19. There we go. x1's gone. All that's left is an x2 here, x2 here. And I'm going to just use algebra, and I'm going to isolate x2 and figure out what x2 equals. Because x1's gone. We can now figure out what it equals. 2 times 8, to get rid of the parentheses, is 16. 2 times negative x2 is like 2 times negative 1 minus 2x2. I still have plus 3x2 equals 19. Now I'm using algebra to put like terms together. I'm going to take the x2's and put them together. I'm going to put the numbers together over the other side. I'm subtracting 16 on both sides. And I'm going to take these 3x2's and these negative 2x2's and combine them, which will leave me with 1 positive x2 on this side. Minus 16 over here, that's gone. Minus 16 over here equals 3. I just found out that on this axis right here, 1, 2, 3. 3 is where that point, where these two lines are crossing, is at 3. I got to find that other one now from the horizontal axis to see what the exact point is. That point's going to be is represented like this with parentheses with 2 numbers. Always the horizontal axis on the left, vertical axis on the right. The vertical axis is a 3. All right, now I'm going to take that 3, which represents x2, and plug it into either equation. The original equations, it doesn't matter which one, whichever one's easiest for you, and solve for x1, the opposite variable. It's obviously going to be easier if I use this one right here. x1 plus x2 equals 8. I'm replacing x2 as 3. x1 plus 3 equals 8. Subtract 3 on both sides. x1 equals 5. Right? x1 equals 5. I now go 1, 2, 3, 4, 5. I go right here. Those 2 lines are crossing right there at 5, 3. Okay, I got to erase this so we can do it again using one of the other methods. Everybody got everything they need out there? Looks like everybody's okay. You want to take a picture? Go ahead. Got it? Hope that zooms in. You ready? So now I'm using the same equations. I'm just getting all my little stuff out of here. Okay. All right, here we go. We're going to use that was the substitution method. We're going to use the addition method. Now, we're skipping the subtraction. Subtraction method. I want to point out, subtraction and addition method are almost exactly the same thing. You almost have to do them the exact same way as far as the logic is concerned. You'll see in a minute. We're going to do the subtraction method now. Subtraction method says you have 2 equations. If you subtract one equation from the other, will it get rid of a variable? For example, this equation has 2x1. This one has 1x1. If I subtract them, it still leaves me with an x1. x1's not gone. Well, what about the other variable? 3x2. This one has 1x2. If I subtract them, it still leaves me with 2x2. Variable's not gone. If one of the variables would have disappeared, I could have just subtracted these equations and solved for the variable that's still left. But I can't, so what I have to do is change one of the equations that will then create the opportunity that when I do subtract them, one of the variables will be gone. And I know if I subtract 2x1 and 2x1, it would be gone. How do I make this x1 into 2x1? I'd have to multiply it by 2. If you do anything to an equation, you must do it to every part of the whole equation. So if I'm going to multiply that by 2 so that when I subtract it, it's gone, I have to multiply this whole equation by 2, not just part of it. So 2 times x1, I'm going to put right here what it turns into. 2 times x1 is 2x1. 2 times x2, positive 2x2, equals 2 times 8, 16. This equation is now gone. It turns into this equation, 2x1 plus 2x2 equals 16. Now I take these 2 equations, the top one and the one that just got turned into here, and subtract them. Here's what happened. 2x1 minus 2x1 is 0x1s, x1's gone. 3x2 minus 2x2 leaves me with 1x2. 19 minus 16, 3, x2 equals 3, the same thing equaled when we used the substitution method. I now plug in 3 to either one of the original equations, and it will say x1 equals 5. You get the correct answer no matter what. Put 3 into the top one for x2. 3 times 3 is 9, right? And we have 2x1 plus 9 equals 19. Subtract 9 on both sides. Now that's 10. Divide both sides by 2. x1 equals 5. You could put 3 to this equation or that equation. You're going to get 5 for x1. And now the last possible way of doing it is the addition method, which is just like the subtraction method. I'll give you one more minute here. Anybody need additional time? Okay. Okay. Oops. Okay, here's our two equations. 2x1, 3x2 equals 19. x1 plus x2 equals 8. If I were to add these, I want one of the variables to cancel out. But 2x1 plus another x1 is 3x1. 3x2 plus another x2 is 4x2. A variable doesn't cancel out. But I know that I could get x1 to cancel out if this x1 had a negative 2. And the only way I can get a negative 2 with that is if I multiply it by negative 2. But if I multiply that by negative 2, I've got to multiply the whole equation by negative 2, just like before. So now the whole equation becomes negative 2 times x1 is negative 2x1. Negative 2 times 1x2 is minus 2x2 equals negative 2 times 8, negative 16. This equation is now gone. It became this equation. I add them. 2x1 plus negative 2x1 is 0x1s. 3x2 plus a negative 2x2 leaves you with just one positive x2. And 19 plus negative 16 equals 3. Exact same answer again. You plug it in either equation, you'll see x1 equals 5. Okay. Whichever process you use, substitution method, addition method, subtraction method, they all give you the right answer. It's whichever one kind of jumped out at you is the easiest. For me, sometimes the substitution is the easiest, but if I see that if I add equations or subtract equations and they will make one of the variables 0, and I don't have to multiply an equation times something to change it all, I'll jump to addition or subtraction and just go for it because it's automatically going to make one 0. It's really fast that way. So. But whichever one you feel. You only are going to have to show me you can do this one time on this quiz 2, and you never have to show me you can do it again. You just got to hang on to it for a couple more weeks. I have a nice example in front of you. Okay? And on your homework. I think you got more time to do this. All right. Now, we're going to review graphing. Let's graph one of these real quick. Let's do this one. Well, let's do this one at a time. Let's do this one right here at a time. The easiest way to graph an equation is, when it has two variables like that, is to make one variable 0, solve for the other variable, then go back to the original equation, make the other variable 0, and solve for the other variable. And what you're really doing is you're finding 2 points on the graph where this equation crosses the axis. Here's our horizontal axis, our vertical axis. We're trying to find a spot where these equations, if they were lines, cross the axis. So, this equation up top, right here. Let me get all this out of the way so using it anyway. Ready? I'm going to go ahead and make x1 0. So this is going to be x1 on this side, this is x2 on this side. And then I'm going to go back and make x2 0. So I'm going to make x1 0, see what that becomes. Then I'm going to make x2 0 and see what that becomes. So what did I say, x1? So this is going to be a 0 right there. And we all know 0 times anything is 0. So what happens is that's gone. And now all you got to do is solve for that. 3x2 is equal to 19. I divide both sides by 3. x2 equals, let's see, 3 times 7 is 21. 3 times 6 is 18. So 6.3333. Anybody got their calculator? Confirm that for me. 19 divided by 3. 3 times 8, that makes sense. 6 times 3, it's got to be, yeah, there's only one left, right? Okay, so I'm going to graph it now. Horizontal axis is at 0. The vertical axis is 6.3. 1, 2, 3, 4, 5, 6. A little bit above there. There's that one. Now I'm going to put a 0 in for x2, right there, which will end up canceling that out. And all I have left is 2x1 equals 19. Divide both sides by 2. x1 equals 2 times 9 is 18. So 9, that leaves 1. 9.5? Calculator? 9.5? So this is 9. Where am I? What happened here? This is so quickly. There we go. 9.50 is x1 ended up at 9.5. 1, 2, 3, 4, 5, 6, 7, 8, 9.5. Now remember, this line is also supposed to go through 5, 3 because we already know that that line is crossing that point because we did the math when we calculated where it's connecting with another one. Now, you should use a straight edge. Never do what I'm about to do. It will never turn out. That was lucky. Extend them. Extend your line. Actually, it's not bad for me. Really good. All right, got it? That's how you graph it. Let's do another one. What was that other equation? Whoops, don't erase, someone say. Still right? Let's do the other one. The other one was x1 plus x2 equals 8. Let's get this all lined up here. We're going to make x1 0, solve for x2. We're going to make x2 0, solve for x1. So if I make this 0, I'm just going to cover it up. x2 equals 8. This is too easy. If I make x2 0, there's no dividing. x1 equals 8. So this line crosses at 8, 0 and 0, 8. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 0. 1, 2, 3, 4, 5, 6, 7, 8, 0. And this line goes through that point of 5, 3. Because we know that from when we did our math. Hang on a minute, I gotta hit this. Oh, that's awful. Believe it or not, that's supposed to be going through that point. So when you copy this, make it go through that point, please. So here's what we're doing. You ready? We have a problem. We figured out what the objective function would be, what the constraints are. We got 3 constraints. We got an objective function. We got 2 variables, x1 and x2. Just look at that. You're familiar with this equation. You're familiar with this equation. So then we go, okay, we want to solve this. What is that optimal solution? What should x1 equal? What should x2 equal? Whatever it represents. Let's graph each of the constraints. Now, at this point, I've been showing you how to graph a line. But when you graph an equation that has the less than or greater than with it, you make the line and then you're shading either one way or the other based on if it's less than or greater than. All right, so since we've done 2 lines, let's talk about this first line, which was, what was this one, 9.5? Which one was it? So I know this one's 8. Is that 8? Yeah. So we're going to do that first one, the 2x, 3x. We got that line here. What I always do to figure out which way to shade that line right here, this one, is I pick a point on one side or the other. And then I take that point and I plug it into the equation, and if it is less than or equal to 19, that must be the direction I shade. If it's not, then that's not the direction I shade. I don't need to do any other math. The opposite direction would be the way to shade. I'm purposely picking a point out here because I know it will be the opposite. I want you to see it. What about, let's see, let's say we go with, what is this, 9, let's go with 9, 2. Everyone agree 9, 2 is on that side of the line? 9 is x1, 2 is x2. So if I put a 9 in for x1 and 2 in for x2, let's do the math. 2 times 9 is 18, right? 3 times 2 is 6. If I add those together, are they less than or equal to 19? Yes or no? Can't hear you. No. No. So we do not shade that direction. The less than equal will go this direction, which is, I gotta make sure I do the right line, which is like this direction, right? Hang on. And I keep going, but I'm stopping on purpose. I'll keep going. Okay? There we go. Now let's look at the other one. x1 plus x2 is less than or equal to 8. That's this line right here, 8 up to the 8 here. I'm going to pick a point on the left side for this one. And my favorite point to use, I use it very often, is right there, 1, 1. I love that one. It's definitely on the left side of that line, right? If I plug in a 1 here, and I plug in a 1 there, 1 plus 1 is 2. Uh-oh. Is 2 less than or equal to 8? Yes or no? Yes. That tells me that's the direction I should be shading. I don't have to worry about the other direction. So now that line, I'm shading this way. There we go, the same direction. And now there's a third one, but it doesn't have the other variable. It only has one variable, and it says it's less than or equal to 6. x1 less than or equal to 6. And it's basically saying that as long as x1 is 6, x2 can be any number. Because it's not even a variable on there. So what I do is I pick 3 numbers, and I make my x1 6. Because if that less than weren't there, x1 has to be 6. Let's just go with 1, 3, 5. How's that? And then you graph it. 1, 2, 3, 4, 5. Okay, 6, 0, 6, 1, 6, 3, 6, 5. And it ends up being a straight line up and down because the other variable's not there. I gotta figure out which way to shade. Are you ready? What point is this right there? That is 7, 7, 3. Let's plug in 7 for x1 and 3 for x2 and see if it's true or false on this. There is no x2, so we're not plugging in the 3. x1 is 7. Is 7 less than or equal to 6? No. We're not shading that way. We're shading this way. That represents the less than. Now, I just put 3 equations on it. Formed lines. Extended the line. I shaded to represent the less than or greater than. These happen to be all less than. Your next step is to identify where every single constraint shadings overlap. Not where just 2 of the constraint shadings overlap, or if there's 6 constraints, not where 5 of them overlap. Every constraint, excuse me, where every single constraint shading overlaps. All of them. In this case, 3 shades have to be overlapping. And you got to identify that area. If you look, that area is right here, not that area there, not that area, none of that, but down here, below my pen, and then we get here, and then it kind of goes like this, and then it goes like this, and then all of this. Your optimal solution will always be in this positive quadrant of a graph. Your variables will always be positive this whole semester. We're not even heading towards the possibility of negative variables of your decision variables. And we're about to learn that sometimes your graph line's way down here, but you extend it up into this quadrant because this is where your optimal solution is. Because our variable that we're making decisions on will always be 0 or positive. You ready? Here's what we just did. We went ahead and figured out x is less than or equal to 6. First we made it equal to 6, and we picked points, 6, 0, 6, 1, 6, 3, 6, 5, 6, 6. Then we shaded. We picked a point on either side, shaded this direction, right? Then we took the next one, and we found out that it crosses the x's at 9.5, 0 by plugging 0 in for one of the variables, solving for the other. Same up here, 0, 6 1/3. We connected the two, And we figured out which way to shade by picking a point on one side or the other, that one. Then we did the x plus 1, x plus 2, or I'm sorry, x1 plus x2 equals less than equal to 8. We found that it crosses the axis at 8, 0 and 0, 8. Connected it with a line, figured out which way to shade, picking a point. Here's our shading. Then, and my advice is, for this one chapter, that the only time you're going to have to do a graph coming up, make your shading really light. Then when you see it's overlapping, this is the best way to show that you can identify what's called the feasible region. Feasible region is the area where all the constraint shades overlap, all of them. And you are for sure in your future have to identify the feasible region. You're going to be given some constraints and say, and you're seeing a graph and it's going to say, identify the feasible region, and you've got to draw, outline it for me like this. And some people like to shade it in dark so that this is the feasible region. They're shading out here, but those are not, because they're not all overlapping. And some people like to even put FR arrow, feasible region, right there. That's what you're identifying. The optimal solution, the one that will be the best possible, is in that feasible region. We've identified, we narrowed it down, but it's pretty big narrowed down. And actually, the optimal solution, here's our feasible region. I know ours is sloppy, but there's a little empty triangle right there. You can't see on ours. I tried to make it. But this is the area. The optimal solution is always where two lines are crossing, at least two lines are crossing, and touching the feasible region. Everybody hear that? How many possible spots do you see two lines crossing, touching the feasible region? No. Not two. Look at the whole graph. Look at the whole feasible region. I see two lines crossing right here. There's one. Now how many? 5. Right here it's 0, 0. This one's easy to identify. Right here it's 6, 0. This one's easy to identify because we graphed it. It's a 0, comma 6 1/3, I think, 6.33. And then these two. Everybody goes, oh, I know what this and this is. I can see. No. These two, you would have to use either the addition, substitution, or subtraction method to figure out these 2 points right here. By saying, okay, what two lines are making that one, and what two lines are creating that one. And in the old days, if all we had was 5 points, we would quickly, I mean, we knew what this point, this point, this point is. We just got to do the math on these two. Then we plug in every one of these 5 points into the objective function. And if it's a max, whichever one of these 5 points give us the biggest number, there's your optimal solution. Go. Fine. Yeah, we have done this. Yeah. We jumped ahead. Is that what you're asking? Yeah, but don't tell everybody. It will click for everybody a little bit. Hang on. You ready? She's already saying, she's already identified where the optimal solution is. So, let's go with this one right here, 0, 0. This is the long way of doing it. You ready? Go back to this. Objective function is a max. I put a 0 in for x1 multiplied times 5. Put a 0 in for x2 multiplied times 7. I get 0. All right, there's our first one. We got 4 more. You know, I just want to show you how this works out. Right here, this is 6, comma 0. Go back to our objective function. 6 times 5 is 30. 0 times 7 is 0. 30. That beats 0, 0, so the point 0, 0 is out. We got it down to 4 now, right? And you just do it like that, and that you can eventually find which one of those 5 points will give you the max for the objective function. What we're calculating, by the way, is called the objective function value. You have a question in your future that says, calculate the objective function value. It means that you plug in the numbers in for x1 and x2 and see what it calculates out to. And you actually plug in the optimal solution for x1 and x2, or whatever the variables are, to get the objective function value. We haven't quite figured out the optimal solution yet, and we don't know what these 2 points are. Here we could put in 0, 6.33, calculate it out. It's more than what 6 comma 0 was. Now that one's out. Now that 0, 0 is already out. Maybe this is the biggest one now. So now we got it down to 3. But we got to say which 2 equations form that. Well, it's this x equals, x is less than or equal to 6, and this one, which is x1 plus x2 less than or equal to 8. And we would do the substitution or whatever method to figure out what that point is. This one up here is x1 plus x2 is less than or equal to 8, and 2x plus 3x2 is less than or equal to 19. We have spent the whole time at the beginning of this lecture doing those 2 equations to figure out what that point is right there. And we did, and she just told us that point is 5, 3. So we don't know this one. We know it's 6 something, right? I mean, the 6 is obvious. Here is a fast way, because you're going to get to where when we have lots of constraints, you're going to get to a point where there's too many extreme points. These are called extreme points. They're the points touching the feasible region on the outside. There are 2 lines across it. There's going to be too many of them. So the shortcut is that you take this objective function and you make it equal to any arbitrary number that's easiest for you. And everybody could use a different number. This is arbitrary. And really what you're trying to do is find the slope of that objective function if it were a line on the graph. And once you have the slope, it will help you identify where the optimal solution is. So, now, I want to add to this. When I pick a number to set the objective function equal to so I can graph a line, I like to pick a number that I look at the numbers with the variables and I say, what would 5 and 7 both go into to make this easy for me? And I go, well, 5 times 7 is 35. 7 times 10, because 5 goes into 10 twice, that'd be 70. So you can use 70, you can use 35, you can use... I try to find numbers that 7 goes into evenly and hope that 5 does too, type thing, just to make it easy. But another thing I try to do is if I pick a number too small or too large, I like to have my line touching the feasible region. You may end up with your line out here somewhere, and you can still do it with your line out here. I personally like to have my objective function line touching the feasible region, so I'll try to sit there and stare at it to pick a number that will make that line touch it. So 35 does it, I already know. I'm going to make the objective function equal to 35. I'm going to figure out where it crosses the axis, and I'm going to draw the line so I can see the slope. So 5x1 plus 7x2 equals 35. I'm going to do my zeros again. Again, here we go. 0, comma something. Something comma 0. I'm going to plug a 0 in for x1, so I'm covering up the 5x1, and all I have left is 7x2 equals 35. Divide both by 7, I get 5. So it's crossed this objective function. I went too fast, I can see some people's faces. You ready? 5x1 plus 7x2 is the objective function. I made it equal to an arbitrary number 35. I picked out the error just because I knew that 5 and 7 both go into it evenly. 5 times 7 is 35. This just makes it easy. You don't have to pick 35. And you don't have to come out with some even numbers. Whatever. No matter what number you pick, every one of us will have a line that is parallel with each other. It's all about finding that slope. And no matter what number you pick, your line's just in a different spot, but they're exactly parallel with each other. The slope will be the same for all of us. I want to make sure you guys understand this. There it is, if I pick the number 35. We were this far, we got 0, 5. If I put a 0 in here, I put a 0 in here, and we divide both sides by 7, we got that 5. If I put a 0 there, and we divide both sides by 5, I get a 7. And then I connected the two. Now watch what happens when I make it equal to a different number. 39. Right there. I made it equal to 42. What is different about these lines is that they're equal to different numbers, but they're exactly parallel to each other, and that's really all you need. You only need to do it once to get that parallel, to get the angle of it. Because once you have the angle, and if this is on paper, any straight edge, this is actually too small for the screen, but any straight edge, and you go, okay, if this is a minimization problem, all the points down here will make the objective function smaller. So I need to go this direction. So either there, And that's it. Those are the only ones are optimal solution. But this one, the objective function's a max. And all the extreme points out this direction are making the objective function better. So my optimal solution is somewhere over here. I'm going to take this line. If I had a straight edge, I would keep it parallel. And if this line could leave, if I had a big ruler, and you see this ruler leaving the feasible region, the very last little spot that line would be touching the feasible region is right at the optimal solution. I keep moving it, I keep moving it. Look at the last spot it's touching. There's your optimal solution. And this was almost the optimal solution. But as you can see, as long as you have a good straight edge and you're staying parallel with the line, that's the last spot it touches. So there's this one, this one, this one, this one, this, out of these 5, there it is. And now, you go, okay, you go back. My optimal solution is right there. So I just need to know what that point is. And you go, which lines are forming that? Oh, it's the x plus x2, 8, and it's the 2x plus 3x2, 19. If I use the substitution, addition, or subtraction method to figure out where those 2 lines are crossing, I found the optimal solution. And we did. And it happened to have been 5, 3. The question, don't stop there. You found the optimal solution. x1, make 5 of those. x2, make 3 of those. The next question is going to say, calculate the objective function value. Where's the objective function? Not on the screen, hang on. You take the optimal solution and plug it in for the variables in the objective function. 5 times, what's the optimal solution for x1? 5? 5 times 5 is 25. 7 times, what's the optimal solution for x2? 3? 3 times 7 is 21. 25 plus 21 is 46. If 5 and 7 are representing profit, we're scheduling 5 x1s, 3 x2s for this next week's production, and our maximum profit we can achieve is 46, this is in thousands, $46,000. And that's the most. There may be another solution that will get you 46,000, but there's not another solution that will get you more than 46,000. It's called alternative optimal solutions. In this class, you just need to find one optimal solution, and that's it. Because when you calculate the objective function value, that's either as big or small as it's going to get, so there's no reason to find an alternative. And that's the best you can do. So that's how you make sure and not waste money. You don't do trial and error. Maybe we should make 6 and 2 or 6 and 4. Let's see what happens. You start plugging everything in. Will that be the most profit? Will that be the most profit? You use a mathematical formula, you plug it into a software you're about to learn or Excel you're about to learn, and it will give you the optimal solution, and that's how you schedule things, and that's how you plan things, by getting the optimal so money's not wasted, so your costs are always in balance. Okay, we're going to do one more. You ready? This one is a minimization. You got to find it. Is that passing? Where is it? There. Here we go. Didn't go fast. I'm going to start by graphing. Okay, go. You want to speak up? I'll make a scene. I made it work. Got to graph these. So, what I want to do 2x1 plus 5x2 greater than or equal to 10. What's the first thing I should do? Oh, huh? Make x1 what? 0. Good. Love it. Make x1 0. Solve for x2. Here we go. I'm just going to make x1 0. Solve for x2. Divide both sides by 5. I get a 2. Sound right? Anybody else? Now I want to know x2. Make it 0 now. I want to solve for x1. So I'm going to put a 0 in right there. Divide both sides by 2 and get a 5. So now I got 5, 0. And I'm going to graph those. Let me see if there's a graph on here. There we go. This is this one right here. Here's 5, 0. Here's 0, 2. All right? Got it? Then, hang on. Let me go back up here. I'm going to, where am I? 1, 2, 3, 4, 5. This is just, there it is right there. I'm picking a point on either side of this line. I'm going to plug it into the equation to see which way to shade. I love to go with my 1, 1. It's always my favorite. So I'm going to put 1, 1 in here. 1 times 2 is 2. 1 times 5 is 5. 5 plus 2 is 7. Is 7 greater than or equal to 10? So that's not the direction you shade. This line's going to be shaded this way, upward. And then you do this with the second one. Plug in a 0. I get -1 greater than or equal to 12, or equal to 12. Divide each side by -1. Uh-oh, I got a negative. X2 is -12. Let me get here. -12, 0. Now, this is one of those situations. 0, -12 is way down here. Let's get the other point, and I'm going to show you what to do. Because you've got to get that line, wherever the other point's at, into that quadrant up there, where both variables would be positive. So now I'm putting a 0 in for the second one here, divide both sides by 4, and I get a 3. So this one is 3, 0. So I got to put a point at 3, 0, and 0, -12. And it's way down here, okay? And it's way down here. I'm extending it into this quadrant. And then I got to figure out which way to shade. Even though my points were not even in this part of the graph, I extended my line when I connected the dots into that part of the graph. And figure out which way to shade. And then you do the same thing with this one. 0, 4, 4, 0, right? Or 0, 4, 4, 0. Right there, figure out which way to shade. It's a greater than, so it's probably going that way. You got all your shadings really light. And then you start looking at where do they overlap. And that's what this is showing you. This shading was going up, this shading was going up, and that shading was going this direction. And they all overlap only right here. Now look at this little intersection thing going on here. I don't know if you can see this from back there, but that little triangle is not part of the feasible region. It's 2 of them are overlapping there, but not the third. So you've got to be on this side of that, where all 3 overlaps are overlapping, where all of them overlap. Somewhere in here is our optimal solution. And it's going to be always at an extreme point. And my question for you is, how many extreme points are there in this particular situation? Not all at once, because I couldn't do it. How many? There's 3. There's 3. There's 2 of them right there. There and there, and then that one there. 5, 0, this one, and that one. And we could do the math on these equations to figure out what those 2 points are, plug them into the objective function. This is a minimization, so whichever one would give us the smallest objective function would be your optimal solution. Or we could go back to the objective function, 5x1 plus 2x2. Give me a number that you might arbitrarily make that equal to. 10, that'd be the easiest, right? 2 times 5 is 10. What else, though, could these handle? 20, 30, anything that both 5 and 2 go into would be the easiest way, right? Whichever one you pick, even if it's, let me get my graph again. Even if your line ends up being way over here or way over there, you know, start figuring out which way you got to go and where your optimal solution is, so you know which way to use a straight edge. And sure enough, we graph it, in this case, using the number, well, remember, I don't know what they made it equal to get right there. Well, it looks like the point is 4.5 and some large number up there. So they used, this is an example where a bigger number was used. What was it? They used 20. They made it equal to 20. 20 divided by 5 is 2. 20 divided by 2 is 10. So that's why it's way up there. 10 is way up there. Right? I don't know why it's right there. Anyway, 5 divided by 20 is 4. I don't know why it's 4. Doesn't that seem off a little? It does, doesn't it? Anyway, there's your line. And this is a minimization problem. When you look at this side, you look at this side, you go, well, this extreme point's on this side, but it's got to be a larger objective function outcome than either of these 2 points. So my optimal solution's got to be one of these 2. And if you had a straight edge, you'd be seeing which one of these 2 points would be the very last one it touches if that line were leading. I'm going to try to stay parallel. Am I parallel? going, hang on. We gotta make sure I'm parallel. Look at, I'm passing one of the points right now. Which one am I passing, the top or bottom one? Bottom one, so the top one would be the very last one I touch. You guys agree? That's your optimal solution. What two equations form that point right there? This one, which is x1 plus x2 greater than or equal to 4, and this one, which is 4x1 minus x2 greater than or equal to 12. I take these two equations, I apply the substitution, addition, or subtraction method, and that optimal solution right there is 16/5. Help me out, that's 3 1/5. 3.1 something? What? No, stop. 16 divided by 5 is 3.2? Okay, 3.2. And 88 divided by 5, which would be what? 17.6. There's your optimal solution, right there. We take the objective function, we plug in 3.2, and this reduces down to 4/5. Wait a minute. Wait, I'm sorry, it is 4/5, my fault. You then multiply, add, there's your objective function value. Now, what is it? 5 goes into 88. Is that what you just gave me or not? What did you give me?
88 divided by 5.
What is what?
17.6.
The objective function value is 17.6. Is there another digit after 6?
Nope.
Okay. And sure enough, 88 fits is probably the objective function value. So your optimal solution is 16/5 and 4/5. I turn them into decimals though. Plug them in, the objective function value, you got it. This is the lowest we can get this cost to. That's it right there. That's what this objective function is. We're scheduling or we're planning on 16/5 of those and 4/5 of those, and this is the lowest we can get our cost. This is a minimization problem. And there may be an alternative solution that will get us just as low as it costs, but there's no alternative solution that will get us better than 88/5 in cost. That's as low as it can get. And that's what the optimal solution is doing for you. All right, watch this. You ready? When you use Excel, I posted this for you, and not only this has more than 2 variables involved, so you'll be able to use this down the road as we start getting bigger problems. I'm just using these first 2 columns here. The top part of this is where you enter your data. Constraint 1, here's the 2 variables we're using, x1 and x2. This is that first example on the very beginning of the PowerPoint. There was a 1 with the x1, a 0 with x2, and if I recall, it was less than or equal to 6. Right? The second one had 2 with x1, a 3 with x2, and it was less than or equal to 19. The third constraint was a 1 with x1, a 1 with x2, less than or equal to 8. And then the objective function had a 5 with the x1 and a 7 with the x2. These cells, you leave 0. We're only using 2 variables, so your optimal solution will appear here. We're going to tell Excel, please put the optimal solution in these 2 locations. This is where you guys start putting formulas. How would you calculate the objective function value? Whatever the optimal solution is for x1, you multiply it times the number with x1 in the objective function. So if you were to write that out using cell location, it'd be E14 times E10. And the 7 is with the second variable. Whatever the optimal solution is for the second variable would be multiplied. So F10 times F14, and then you add them together. And when you look at this, when you go home and you say, what formula is in there, you'll see exactly what's going on. E10 times E14, E10 times E14 plus F10 times F14. That gets the objective function value. I only take the word max there because it's a max problem. If this is a min problem, just change it to min or just take it out of it. Now, here is where you would write the formulas for the objective function. If I wanted to know, if I place the objective function into this constraint, if I place the optimal values into this constraint, will it be less than or equal to 8? So let's see, I'm putting, what was the optimal solution for x1? A 3 or 5? 5? 5. If I put a 5 times 1, that would be 5. If it's 3 times 1, that would be 3. And I add them together, you get 8. And right here, that's exactly what this formula is doing using cell locations. It's taking E9, where that 1 is, with x1, times the optimal solution, E14, and adding F9 times F14. There's the left side. Now, I typed those in just to remind myself that this one's a less than equal. And then if it's a greater than equal, you would just change those just for visual. That has nothing to do with Excel. I just do that for visual. Here, I have those be cell locations because when you're entering your data up there, if those numbers are different, this will change automatically. So this equals J, what is that, 6? J7, this one equals J8, this one equals J9. Then you've got everything in place. You go to data. By the way, follow the steps on page 89 in your textbook. If you have an older edition, it's right near 89. Take a picture of someone else's so you know where to find it. Data. Then go to solver. Don't forget, if you don't have solver, either use lab anywhere, to use the computer at the lab from home, or install solver. Just go to help up there, say install solver, and it will give you step-by-step instructions. File, options, add-ins, I think. Where's solver? Solve add-on right there, you go on and on. Blah, 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 blah. You ready? Follow the steps on page 89. Solver. Then it says, hang on, I get rid of these. Then you can't see these. Hang on. All right. Comes up blank the first time. The word set objective means what cell location do you have your formula where you're calculating the objective function value. Making sure it's the right cell. So where is that? Right there. E16 is where we're calculating the objective function value. Now look, if this is on a quiz, you're going to see a picture that looks exactly like this. And I'm going to ask you, what would you enter where it says set objective? So I hope you have your notes. That means where the objective function value cell location, where it's being calculated, which in this case is E16. Next, click whether it's a max or a min. This one happens to be a max, so I'm leaving it right there. Next, by changing variable cells, I'm going to left click there, and I'm just going to highlight the cells where the optimal solution needs to be placed. Excel will constantly change the optimal solution cells when I tell it these two cells until it figures out the very best solution. And it does it in a split second. These numbers are going just like in a second, and it will find the optimal solution. I got to tell it where to change the numbers. Where is the optimal solution at? E14, F14. So I'm just highlighting them and drag, and there it is, E14 colon F14. $, so it doesn't change if you want to put $. Next, subject to constraints. It wants to know, this is the hard part, where the cell location is that you're calculating the left side of constraint. Then you got to tell it, is it a less than equal, greater than equal, or equal? And then tell it the cell location where the right side of this constraint is. The left side of our constraint's here, and the right side of it is there. Let me get this out of the way. Everybody see it? So we're going to do the first constraint, which is this cell location and that cell location. Again, let me put this here. Right there. Add constraint. Reference cell. Where's the left side of that constraint? It is right there. The first one is E20. Then you open this box. Equal to, less than equal to, greater than equal to. This one is a less than equal to. Then constraint right-hand side is going to be this box right here, which is J20. So I got J20 on the right over there, I got E20 on the left, and I told it it's less than equal. Click OK. That constraint just showed up here. I got 2 more constraints to go. I'm going to hit add, go a little faster. The left side is right here, this time it's E21. This constraint is also less than equal, and the right side is J21. Hit OK. There's my second constraint. Got one more. Go faster. Here we go. Left side, right there. Less than equal already. Let's go over here to the right side, which is right there. Hit OK. There's all three of them. And there's a shortcut you can do all. You can combine less than equals together. Well, I won't go there yet. So there's all three. Next, this box right here must be checked. We are using non-negative variables this whole semester. Our decision variables will always be either 0 or positive number. So always check that box. And this down here, sometimes when you first open it, it will say, whoops, it will say GRG nonlinear. We're using simplex LP, which stands for linear programming. So always make sure that, and that's it. Let me repeat this. Make sure that box is checked. Make sure this is on simplex linear programming. When I hit solve, it's a split second, and then it comes up with this box that says OK. Just click OK, and you'll see your optimal solution. You ready? That's it. Our optimal solution will always be right here, 5 and 3. If we place 5 and 3 into constraint 1, the left-hand side would be 5, which is a little less than what the constraint was less than equal to. If we place 5 and 3 in with constraint 2 for the variables, it equals 19, which happens to be what the right side was equal to. And when I see the left side and the right side the same, I know that that's called a binding constraint, B-I-N-D-I-N-G. Binding constraints are, out of all the constraints, the ones that form the optimal solution are the binding constraints. And the left-hand side always ends up equaling the right-hand side for a binding constraint. Easy way to recognize it. The third constraint, if I put in 5 and 3 with the variables, the left side equals 8. It's just a coincidence. Look at this. The right side equals 8. We found what kind of constraint here with the third one? There's 2 binding constraints, and it just so happens the binding constraints, these 2, were what was crossings where 5, 3 met, which is where that optimal solution was for that first example. This top constraint is not a binding constraint, and its number will always be different than the right side, and the difference we're going to talk about in the next lecture. That's it. We went a minute over. I owe you a minute. Wait, you owe me so many minutes that now we're not even close to eating yet. Thank you. See you next week. We have an in-class on Monday, homework due on Wednesday.